6.2 Graphs of exponential functions. Now this section in the textbook is much lengthier than what I'm going to go into, and I'm going to do that mainly because we've seen transformations I think twice before, at least once before. So if this lecture seems like a big struggle, go back and view the lecture that has to do with transformations when we were dealing with basic parent functions, and we're using the exact same process, just with a new parent function, that parent function being the exponential function. So as a bit of a review, kind of basic properties of, in this case, we're going to be less general. We're going to say straight our parent function is y is equal to 2 to the x. Key points are 0, 1. That's going to be my y-intercept before any transformations. And then if I plug in 1 into my equation, I'll get 2. And if I plug in 2, I will get 4. And so those are going to be our 3 key points when we're going through this transformations. The other kind of parent function is if b is between 0 and 1, and we typically talk about that with 1/2. And the key points for that, I don't think we'll kind of see an example in this section, but the key points for that are going to be, would be, again, 0, 1, and then 1 and 1/2, and 2 and 1/4. The reason that we don't really talk about it much in this section is because it's fractions, and fractions can cause a bit of a headache, but it's perfectly fine. The concepts apply exactly the same. You just have to be careful when you're adding and subtracting. So we talked about it in the very general case, y is equal to a times b to the x, and your horizontal asymptote is y is equal to 0. That is true from both of these parent functions as well. The same horizontal asymptote, same domain, negative infinity to infinity, and the same range that we saw in the last lecture, 0 to infinity. So we got to keep all of that in mind when we're kind of maybe ask questions after our transformations of what's our new domain or what's our range. Or specifically, we like to, in this class, talk about what happened to the horizontal asymptote. So keep those 3 things in mind. X-intercept is none, because we have that horizontal asymptote if y is equal to 0. Y-intercept is 0, comma a, or when we were talking about y is equal to 2 to the x, 0, comma 1. And we don't really talk about that this much in this section. That's why I'm actually not going to fix the error on this one. The graph is going to be increasing if b is greater than 1, and it's going to be decreasing if b is between 0 and 1. So it's that, is it a exponential growth? B is greater than 1. Yes, increasing. Is it exponential decay? Between 0 and 1, then it's decreasing like the graph on the right. So now I have a function. Y is equal to 3 times 2 to the x minus 2. So I can kind of recognize that my parent function is going to be 2 to the x, and I will write down my transformations after I put down my key points. Yeah. So I will write down my transformations, but originally my key point for y equals 2 to the x is 0, 1, 1, 2, and 2, 4. So I'm going to start with those key points, and then just like we did in the transformation section, we're going to describe our transformations. And so the first transformation is I've stretched vertically by 3, and my second transformation is I shift down by 2. Now you might be remembering when we talked about transformations, I'm not super concerned about the terms stretch or shrink because, in my opinion, they are fairly arbitrary. But it is worth mentioning the transformation just when you go through the process, whatever helps you remember what you're doing. So I would, if I was not making a formal slide of this, I would not say it's vertical stretched by 3. I would say multiply y by 3 because that's exactly what you're going to do. But formally, you are stretching your graph vertically by 3. So now we apply these transformations to our 3 key points. To vertically stretch by 3, well, as I just said, we multiply each y value by 3. So my first point will become 0, 3. My second point will become 1, 6. And my third point will become 2, 12. 2, 12. Now I have to apply my next transformation. I'm shifting down by 2, and down is also going to be applied to the y values. So I'm going to subtract 2 from each of my y values. So my first point now becomes 0, 1. my second point becomes 1, 4, and my third point becomes 2, 10. And remember that it's that idea that we talked about in the transformation section of inside and outside. So in this case, the inside would be my power, and so if I'm doing anything to the inside of my function, I would be applying that to my x values. And then outside of my function, outside of my 2 to the x, is where I'm going to apply things to the y values. So in this case, it just so happens that both of my transformations were outside of my parent function, and so that's why I'm only applying them to the y, but it's not always going to be the case, so be aware of that. And from there, I'm going to plot my points. So one of my key points is now 0, 1. One of it is 1, 4, and the other one is 2, 10. And I know my graph shifted down by 2, so I will have a horizontal intercept at y is equal to 2. And finally, I know the shape of my graph. It's 2 to the x, so it's that exponential growth, almost that like swoosh to the positive section. So yeah, it might be tricky to think about what an exponential function looks like, but really we're playing that game that we've played several times in this course of connecting the dots. I'm going to plot my points. I'm going to say my horizontal intercept is y is equal to 2, and as long as you draw a graph that goes through those points and doesn't cross your horizontal asymptote, you'll get full points for the question. Oh, there it is. Kind of hard to see because it got cut off. But it's saying right there at the bottom of the slide, the y horizontal asymptote is y is equal to -2. Now, I could be given a graph, or I could be just have a graph described to me, and I might have to go back and write the actual equation. So in this case, I'm not actually going to do the graph. Instead, I'm going to describe what's happening in the graph. But really, that's only one step removed if you had a graph in front of you. So in this case, we are told we have an equation of e to the x. Well, I don't think we've seen e to the x before. It doesn't matter. It's an exponential. So we're going to just say, okay, now my parent function is e to the x as opposed to 2 to the x. So it's fine. If you are curious, e is a very important number. We see it a lot when we're modeling population, so we give it its own special fancy variable, and I believe it's 2.7 something. I could look that up. So it is an actual number. It's not a variable. It's kind of like pi. We give pi its own value. And so that's what's happening. It is an exponential. It is a value, but instead of writing down a weird decimal, we just call it e. Okay, all of that aside, we want to apply transformations to this graph that is e to the x. I know my horizontal asymptote is now as y is equal to 3, and I also know that it is going to be reflected over the x-axis. Okay, well, I know that if it is a horizontal asymptote of y is equal to 3, well, my graph better be shifted up 3 units. So I'm going to add 3 to my e to the x, so I know at least I'll have e to the x plus 3. And then since it's being reflected over the x-axis, a vertical flip, that means I'm going to multiply e to the x by -1. So if I just connect those two dots, I have y is equal to negative e to the x plus 3. That's it for this section.